Good day, everyone. I am Jojene Santillan from the Caraga Center for Geo-Informatics of Caraga State University in Butuan City, Philippines. I am pleased to present to you our paper entitled A Maximum Entropy Approach for Mapping Falcata Plantations in Sentinel-2 Imagery. This presentation will revolve around Falcata, which is one of the widely planted and most important industrial tree plantation species in Caraga Region, Philippines. This tree species is a significant source of wood for paper, veneer, and furniture production. Here in Caraga Region, Falcata is most preferred by tree farmers because it can grow very fast on various types of soils and can be harvested in 6 years after planting. For several years already, Falcata Plantations has significantly helped the Caraga region to retain its title as the Philippines timber capital. This region contributes to more than 50% of the Philippines' yearly log production. Despite their importance in the country's log production, the types, locations, spatial arrangements, and total area of Falcata plantations in the Caraga region are not well characterized. The spatial temporal aspects of their growth and development, as well as management dynamics, are also not well documented. Hence, efficient and accurate mapping of Falcata plantations is essential for better monitoring and management of these plantations. When we talk about mapping and monitoring tree plantations, several approaches would come to mind. One of these approaches is the conduct of ground surveys. Unfortunately, ground surveys would require more manpower and is time-consuming, making it difficult and expensive to implement. One of the best alternatives available right now is through satellite remote sensing. Using this technology, images of plantation areas can be acquired using sensors on board a satellite. These images can then be analyzed to locate and discriminate tree plantations. This approach is less expensive and best suited for spatiotemporal monitoring of tree plantations because it can be used to map large areas over a shorter period of time and can be repeated over a desired time interval. The remote sensing approach for tree plantation mapping is heavily reliant on multi-class image classification, which is a technique employed to classify or label each pixel of an image into their corresponding land cover classes. While multi-class classifiers perform very well in land cover classification of images, they require training data for all features or classes in the image, thus making it time-consuming when a single species or single class is the only interest. Moreover, these types of classifiers may be inaccurate for single class detection due to incomplete training datasets. So when the main goal is to classify only one class, multi-class classification approaches can be inefficient since all classes that occur in the image needs to be labeled. In such a case, a one-class classifier can be a more efficient alternative. One-class classifiers are binary classifiers that can be used to separate the specific class of interest from all others in an image. It requires only two datasets, training data for the class of interest and a set of known constraints on the distribution of the class of interest. One example of one-class classifier is MaxEnt. MaxEnt was initially developed for ecological modeling and species distribution assessment. It is a machine learning software based on the principles of maximum entropy. As a general-purpose method for making predictions or inferences from incomplete information, it can deal with presence-only data and small sample sizes, thereby reducing the extensive processes involved in multi-class image classifications. However, there are some challenges on the use of MaxEnt as a one-class classifier. Among these is the difficulty to find the best values of parameters to obtain reliable results. Some studies have also concluded that MaxEnt parameterization influences classification accuracy. Among the major parameters that require attention are the training sample sizes and the binary threshold values. And that is where our study comes in. Our objective is to apply MaxEnt for mapping Falcata plantations in Sentinel-2 imagery. Specifically, we aim to determine the effects of sample size and binary thresholds on the accuracy of MaxEnt classifications. Our ultimate goal is to develop a simple but efficient classifier that can be used for mapping and monitoring Falcata plantations. The study area comprises 3 barangays of Butuan City in the Caraga Region, Mindanao, Philippines. The vast distribution of Falcata tree farms in these areas permitted us in collecting a sufficient number of training and validation data points. The barangays also have different topographic characteristics, making them suitable for MaxEnt classification and accuracy assessment. Our methodology consists of training and validation sample collections, Sentinel-2 image data preparation, MaxEnt modeling, application of binary thresholds, accuracy assessment, and application of the best MaxEnt models for the generation of Falcata classification map. The Sentinel-2 image used was acquired on August 10, 2019. It consists of 4 surface reflectance bands. Various vegetation indices were also generated from the image and used as additional data layers for MaxEnt modeling. We also used a digital elevation model and its derivatives in addition to the Sentinel-2 image and vegetation indices. The training data consisted of 1,000 random samples of Falcata points, while the validation samples consisted of another set of 1,000 Falcata points and 4,324 non-Falcata points. MaxEnt version 3.4.1 was used in the modeling and classification. MaxEnt outputs were generated using various sample sizes. Then, various thresholds were applied to each of the outputs to generate the binary classified maps of Falcata. The binary thresholds used include manually selected thresholds from 0.1 to 0.6, as well as various MaxEnt built-in thresholds. And now for the results. Here is an example MaxEnt output. This is a raster file where each pixel can have values ranging from 0 to 1. These values corresponds to the conditional probability of occurrence of Falcata. The higher the value, the higher the probability that a pixel is a Falcata. We can apply a threshold to the MaxEnt output to make a binary classification map, which will separate Falcata from non-Falcata. As for the effect of sample size or training data size on classification accuracy, here is the result. It can be noticed that the higher the sample size, the better the classification accuracy. However, the differences in accuracy values are not that much, which seems to validate the earlier assertion that MaxEnt can deal with small sample sizes, thereby reducing the extensive processes involved in multi-class image classifications. On the other hand, the manual selection of threshold also influences the classification accuracy. Using a small sample size of 30, a 91.87% accuracy can be achieved using a 0.3 threshold. Selecting a threshold higher or lower than 0.3 seems to decrease the classification accuracy. The same can be observed for a sample size of 500. However, there is relatively large increase in accuracy when a bigger sample size is used. Now let's go to the results using MaxEnt's built-in thresholds. The thresholds shown are automatically calculated by MaxEnt. Each of these thresholds were applied to the MaxEnt outputs, and each outputs were assessed in terms of classification accuracy. Here is the result of accuracy assessment using a 500 sample size. The highest accuracy was found when using the equal training sensitivity and specificity threshold or ETRSS. The threshold value is 0.282. Take note that this value is closer to the manually selected threshold of 0.3, which also gave the highest classification accuracy. This result seems to support the manual selection of 0.3 as the threshold for generating binary classification maps. In cases where it is difficult to manually select thresholds to generate a binary classification map, choosing the ETRSS threshold would be a good option as far as the results of this study is concerned. Now, to finally accomplish the purpose of this study, here is the final Falcata map of the study area, where a 0.3 threshold was applied to the MaxEnt model output that utilized a sample size or training data size of 500. We further checked the accuracy of the map by comparing it to Falcata locations that were surveyed on the ground and delineated in Google Earth. The MaxEnt classification map generally agrees with the ground truth data. In conclusion, the study successfully evaluated the maximum entropy approach to one-class classification for mapping Falcata plantations in Sentinel-2 Imagery. Our results show that indeed, MaxEnt can provide reliable classification results. And that ends my presentation. Thank you very much for your attention. And I would like to acknowledge the PICARD, the Science for Change program, and the Department of Science and Technology of the Philippines for their support to this study. Thank you once again.